Okay, AP Physics students. I promised I was going to make a video over break to talk a little bit about the next topic, so that's what I'm doing. I'm going to just do this in a single take, and the only thing I've pre-written is that equation that you can already see, so I'm probably going to make some mistakes and have to correct myself. So the formula that's written there is, as you hopefully remember, the electric field magnitude produced by a single point particle with an electric charge q. And that electric field is a function of position. The electric field fills all of space, and so depending on the position where you want to measure the electric field, you get different values. And the main way in which the position of your measurement matters is because of this distance r. So the further away from the particle you get, the weaker the field becomes, etc. The direction of the electric field is going to be radial. Depending on if q is positive or negative, the field could point inward or outward. But it's going to be radially symmetric either way, as long as there's only one particle. If there are multiple particles around, and I'll make a quick little sketch here. Suppose I have like a few particles all in a line like this. Let's say they're all positively charged for simplicity. Each one of those particles is a source of electric field. But if you want to know what the field is like at some location in space, I'll make a dot like out here. This is not a particle. This is the location where I want to measure the field. I'll call that point P. If I want to know about the electric field at that point, I'd have to calculate the contribution to the field from each of the four particles. Those contributions are all going to be vectors, and I'd have to get the sum of those vectors. That's called the superposition principle. Superposition basically just means adding things together. So there are 4 contributions to the electric field at point P, one from each of the individual particles. So the electric field due to particle 1 is going to be basically horizontal, because they're kind of lined up vertically with each other. It's a little bit off. There. Now it's more horizontal. The electric field due to particle 2 is going to go up and right. Mostly right, but a little bit up. So E2 might look something like that. E3, something like that. E4, something like that. So each of those contributions points in a different direction, and they have slightly different magnitudes also, since the distance from the particle to point P is not the same for all the particles. So E1 has the biggest magnitude, E4 has the smallest magnitude. So like in principle, I could figure out what the total electric field at that point is just by calculating these individual contributions and adding them together. This would not be a pleasant one to do, but like in principle, it's possible. And that's essentially the kinds of questions that you were seeing before February break, the ones that I asked you to do over February break, where you have a collection of particles and you know that each particle generates its own field, you find the total. Now, the trick is, what if instead of a line of 4 individual particles, I have something like a charged bar, a continuous object, and I want to know about the electric field at my point P. That is going to require some calculus. So I'm going to describe the general idea behind the approach here, and then I'm going to do one example. And there are going to be other examples that you will see in the textbook or in other videos that you look up or whatever. There are many, many examples of this technique that you can find. Don't get too hung up on being able to do this particular technique, because there is a better technique, which we'll study next, called Gauss's law. But you still need to have like a basic understanding of how this technique works. So if the bar has a total charge, big Q, as with all of the other integrals that we've done this year, the idea is to imagine splitting that bar up into individual pieces. Like, yes, I'm saying it's a continuous object, but it's still got to be made up of, you know, particles. And so if you just imagine splitting it up into a huge number of tiny pieces, you can treat each individual piece as if it is one of the particles from that previous case. And doing that, you can get all of the individual little pieces of electric field, and you can add them all together. And you can automate all of that with an integral. So I've got this overall bar with a charge Q. I'm going to select just a tiny little sliver of it, that little piece that I just outlined in red. And that little piece has a charge which is much less than Q, because it's an infinitesimal portion. So that piece has a charge dq. The electric field produced by that little tiny piece, I'm going to try to get the arrow in about the right direction. It's going to look something like that, assuming Q is positive. And I'm going to call this, instead of like E1, E2, E3, I'm going to call this dE, because I know that this is just an infinitesimal portion of the total electric field at that location. So, as you might guess, dE is equal to K dQ over R squared. I'm going to drag this P out of the way so I can draw another line in. So that dashed line there is the distance R. R is the distance from the source of your electric field to the location where you are measuring that electric field. So I can calculate dE, the magnitude dE, using that formula. But the kicker here is that if the only thing I were to do is throw an integral sign on both sides, like if I just said, oh, well then I'll just integrate it. The reason that that is not going to work in this case is that electric field is a vector quantity, and so you can't just literally add like scalar values, all of the little dE's, because some of these dE components are going to cancel each other out, and some of them will reinforce each other instead. So you would need to be very careful in principle for a case like this. Let me get rid of those integral signs. Some of you probably already wrote it down. You should not write down those integral signs. So like in principle, what you would have to do is separate x and y versions of this. So like dE x, the x component of dE is k dq, oh no wait, I used a big Q. K dq over r squared times some sort of a trig thing to get just the x component. And dEy, similarly, is k dq over r squared times some kind of a trig thing to get just the y component. There'll be different trig things. So like, you know, one is probably going to be sine and one of them cosine of something. It's going to be related to the geometry of the particular problem. And I drew this particular problem in a really generic way, so I can't I can't like specify exactly what it would be, but I'll do an example where I can be specific. So once you know that you're looking at the individual components, then you can throw the integrals on and you can get a result. So in this particular case, I would do the x version, I would do the y version, and then I would know the x and y components of the total electric field, and then I could figure out the magnitude and the direction or whatever I wanted to know from that. So let's talk about a specific example. All of the examples, all of the problems of this type that you'll have to do are going to have simple geometries with a lot of symmetry involved to make the math easier. So the case that I want to do is with a ring. So this is a uniformly charged ring. It has a radius big R. It has a total charge big Q. And the place where I want to measure the field of the ring is at this point P, which is directly above the center of the ring. So P is on the axis of the ring. I'm going to say that the distance away from the center, or the distance from the plane of the ring, I suppose, is z. And I want to know what the electric field at point P is based on this. So, one thing that you might be able to guess, just from thinking about the symmetry in this setup, is that the direction of the electric field is going to be, assuming Q is positive, it's going to be like straight up. It's going to be in that z direction. Because I have all of these individual contributions to the electric field that are coming from all around the ring. But all of those like horizontal components are going to end up canceling each other out. Some of them point to the left, some of them point to the right, etc. And since it's a uniformly charged ring, all of those horizontal components are going to cancel. But that will leave me with all of the z components, and they all point in the same direction, and they reinforce each other. Now, there is a shortcut version to calculating this, which I guess I'll do the shortcut version first. And then I'm going to show you the like brute force way to illustrate how the integral works. Let me highlight a little tiny piece like I did before. So that little red box is the location of my dq. I know that that dq makes a small contribution to the electric field, which I call dE. And I guess I'll use blue for this. I know that that dE vector has a vertical component DEZ. That's kind of small. It says DEZ. I'll draw a bigger version in a second. And then there's also a horizontal component, which I don't care about because I know that those horizontal components are all going to cancel each other out. And I know that that distance there is little r. That's the distance from the source of the field to the place where you're measuring the field. So I have a little r and a big R. Big R is the radius of the actual object, the ring. Little r is the distance from each individual piece of the ring to the place where I'm measuring the field. Okay. So let me draw a larger version of the dE vector, just to make sure you can see what I wrote. That's the dE. So there's the z component, and then there's the horizontal part. I'll call that x, I suppose. Okay. So again, all of those horizontal parts, the DEX's, would cancel each other out if I added them together for all of the different parts of the ring. So I only care about DEZ. And this triangle that I just drew is similar to this triangle here. And in fact, those two angles are the same. That's called vertical angles, I think vertical angles is the name for that, but they're congruent. So since I'm only interested in the z component of DEZ, I could write that, let me see. So like I could name this angle theta. Ooh, I don't want to use the angle theta. I'll use the name phi. So I could name that angle. And so DEZ would be DE cosine phi, right? DEZ equals DE cosine phi. But since I know that that other larger triangle is similar, I could also write cosine phi as this here is phi. Cosine is adjacent over hypotenuse. The adjacent side is that one. Hypotenuse is this one. So cosine phi is the same thing as z over r, which is also the same thing as z over the square root of big R squared plus z squared. So those things are all equivalent to each other. And even though it's not as pretty, this last one is the most useful because it's written only in terms of quantities that were stated in the original problem. We were told the radius of the ring is big R. We were told we want to know the field, the distance z above the center. Little r is not a quantity that was given in the problem, so our answer should not really contain little r. Little r is the hypotenuse of that triangle formed from big R and z. Okay. So the kind of like clever cheating version of getting the electric field at point P is to say, well, I know that the z components for all of the pieces are going to count, and I know that the x and y components are not going to count because they're going to cancel each other out, those horizontal components. So the fact that this is a ring doesn't really make a difference So the cheating version, I will write the word cheat. The cheating version of the problem is to imagine just putting all of the charge at the location of your dq, and then just only calculating the z component of that electric field. That will work. Again, we have to count only the z component because the other components go away. But that would mean that E is equal to kq over r squared, little r squared. The little r squared is big R squared plus z squared. And then the way I get the z component is to multiply by z over square root of r squared plus z squared. So I could write that as kqz, and then this stuff to the 3/2. I'll put a z subscript on the e, just to emphasize. So like that's the answer that I'm going to end up with when I do the real version of this. So let's actually do the real version. I'm going to go to a new screen. But I want to... How do I paste? That's how. Just wanted to reproduce that stuff. Okay. So if I want to do this with an integral, what I need to do is imagine taking all of those individual DEZs and add all of them together. The DEZ from each individual DQ. I have to take all of those and add them all together. So conceptually, what I'm saying is E is the integral of those z components, the integral of DEZ. And I know that DEZ is going to be k dq over little r squared times z over the square root of big R squared plus z squared. So that first part, that's just the electric field formula, kq over r squared. And the second part is the little ratio that I found over here for the trigonometry. So at the moment, my notation is a little bit mixed. I should try to clean this up. So k dq r squared z squared 3/2. Should probably still include the integral sign also. So it's starting to look like something that I could integrate, but q is not a coordinate. So if you think back to when we were calculating integrals for rotational inertia and integrals for center of mass, when we set those up, we always had a dm, a little tiny piece of mass dm. And that's similar to what I have right now with a little tiny quantity of charge dq. And the way that we always dealt with that, since we have to have a coordinate to integrate over, is that we change the dm into something like a density times a length, or a density times a volume, or something like that. And so the question is, how much charge is dq? Like, how much is that? So it's going to be, in this case, since the object is like a linear kind of thing, it's going to be some sort of a linear density lambda times a length. And since it's on a curve, we'll use s for arc length. So lambda is charge per length. ds is a little tiny amount of length. So you multiply those together, you get a little tiny amount of charge. Lambda itself should be the total charge q divided by the total length. The total length is 2 pi times big R. That's the circumference of the ring. And so I've got, I guess, two choices now. I could leave this as ds, and I could integrate s around the circumference of the ring. So I could integrate s from 0 to 2 pi big R. I could also change the ds to be in terms of theta instead, if you want to think about like a cylindrical coordinate theta that I use to rotate around the axis. I'm going to do it that way because it's a little bit more common to need an angle version instead of a linear version. So I still have q over 2 pi big R. And the ds I'm going to write as r d theta. So that's just using an arc length formula. Radius times angle. So now I have a coordinate on my differential. Instead of being dq, it now says d theta. Theta is a coordinate. And I know that I'd want to integrate theta from 0 to 2 pi. So going back to the electric field thing, E equals the integral of k over r squared z squared to the 3/2. And then for the dq, I'm going to put all that junk that I just found. Notice that the big R cancels, so it looks a little bit simpler. It's q d theta over 2 pi. Q over 2 pi d theta. And I know that I need to integrate the theta from 0 to 2 pi. I mentioned that already. That way it'll get me the whole way around the circle. And as you glance at this, you may think that this is an unpleasant integral to calculate. But that's because you are thinking of integrating it with respect to z or r. But that is not what we're integrating with respect to. We are integrating with respect to theta. And there are not any thetas in the integrand. All of these things are constant with respect to theta. So the integration itself is trivial. Getting it set up was not trivial. I admit that. I had to do a lot of clever things to get to this point. But the actual process of integrating it is trivial. So I'm going to take all of the constants out. kq r squared z squared 3/2. There's a 2 pi also. I'll jam that in front. I'll drag this over a little bit. And then I have integral d theta from 0 to 2 pi. That's the actual integral that I'm left with. The result of that integral is 2 pi. And so the result of the integral is going to cancel out with the little 2 pi that I had just jammed in there. And so that gives me kq over r squared plus z squared to the 3/2. Which, again, is the thing that I said on the previous slide with the cheaty version, where I just kind of pretended all of the charge was in one place. Most of the time, you cannot get away with pretending the charge is all in one place, and then taking only a particular component. Sometimes you can, but so like that's a technique that you can look out for, I guess, a technique you can consider, but a lot of the time it's not going to work, so be careful with it. Okay, so there's a couple of things I want to do with this result. I'm going to rewrite it. E ring equals KQ. Oh, wait a second, I lost my Z somewhere. Lost the Z in that step there. I had it, and then I didn't write it. So I'm going to fill in all those Z's. It doesn't change anything meaningful because Z is constant with respect to theta, just like all the other stuff was, but I do need the Z. Okay, so KQZ big R squared plus Z squared 3/2. All right, so there's a few different things that you can do with this result. So thing number one, consider the limit as big R goes to 0. What that means is that instead of having this ring with a finite radius r, I'm shrinking it down to make smaller and smaller rings. And if it reaches a radius of 0, then the ring has basically turned into a particle. And if you look at the expression that I have, this is an easy limit to do. It's one where you can basically just substitute in. So if I substitute in 0 for r, then in the denominator I have z squared to the 3/2, which is z cubed. And then I can cancel out a factor of z, which gives me kq over r squared. So the particle result comes out of this if you shrink the ring down to nothing. That's always encouraging. When you get a new result, consider a limiting case, and you find that it's consistent with something you already knew. I suppose similarly, if I took the limit as r goes to infinity, so I have the same amount of charge q, but I'm spreading it out over larger and larger rings, one that's infinitely large. If you take the limit of this as r goes to infinity, the electric field just goes to 0. And that's also good, because if all of the charge is infinitely far away from you, the field should be 0. Now, another case is to consider a disk. So if I have a solid disk of charge, how do I want to represent this as being solid? I will fill it in. If I have a solid disk of charge, you can, of course, imagine that that disk is actually very many concentric rings. And so if I were to take my ring result and integrate it with respect to the radius of the ring, I'm going to say that the disk, oh no, I need a different terminology here. let's say I just need any old letter. I'm going to call it A. I should write it in red though so you can see it. So let's call the radius of a given ring A. And the radius of the full disk, big R. So if I just take the expression that I already got, the ring result, and I integrate it with respect to that radius between 0 and big R, I can find the electric field produced by a whole set of rings that are forming a disk. I am not going to perform that integral, but there is a question related to it, I think, in the problem set. It's an integral that's more complicated than is worth doing in a physics class. In a math class, sure, but not in a physics class. But if you perform that, you would get the disk result, which looks like 2kq over big R squared times 1 minus z over R squared plus z squared square root. You don't have to write this down. Another way of expressing that is with a density sigma times this same stuff. Sigma is charge per surface area, just like lambda is charge per length. And if you need a charge per volume, we use a rho for that. These are the same symbols that we used when we were integrating masses also. A length density is lambda, an area density is sigma, volume density is rho. So like, if you rewrite this disk result in terms of the charge density instead of in terms of the total charge, you get this version. And the only reason that I'm bringing that up at all is because you need that version to consider a uniformly charged plane, because a plane is infinite. So if I were to try to consider the electric field of a plane of charge using this upper version, it would diverge because Q would have to go to infinity for the plane. However, if you think about it in terms of the charge density sigma, then it's not so bad, because the idea with this lower expression here is that if I want to turn the disk into a plane, I just need to make big R go to infinity. So for a plane, big R goes to infinity. And from the second expression, that's really easy to see what's going to happen. Big R goes to infinity, then the electric field just becomes sigma over 2 epsilon naught. And yes, it's being written in terms of epsilon naught here instead of k. If you want to write it in terms of k, you can, but the reasons for using epsilon naught here will be more obvious later. But it's usually written with an epsilon naught. So this result is super important. There is a much easier way to get it than to go through this whole chain of reasoning that I've laid out here. First finding the electric field of a ring, then integrating it to make a disk, and then making the disk infinitely large. You don't have to go through all of those steps to get this result. You can get it in the space of like 30 seconds using Gauss's law, which is our next major topic. However, there's a couple of features of this result that I want to point out. Notice that there are no coordinates of any kind in it. Even the z is gone, right? And this expression here for the disk, your distance away from the disk was important, because if you get far away, the field should weaken, and that's what this shows. But if there's an entire infinite plane, then your distance from the plane ends up not mattering, since it fills that entire infinite thing anyway. If you think about the electric field lines, suppose I have, obviously I can't draw an entire infinite plane, but suppose this is just a very large sheet of charge. The electric field of this thing has to consist of parallel lines, parallel field lines. They would go down as well on the other side. But since it's an entire infinite plane, the field lines, they can't like bend away from each other because they would end up crossing lines from further down the plane. So the lines are all parallel and straight, which is the same thing as a uniform electric field. No matter where you go on the upper half, at least, anywhere in this upper half of the universe, the magnitude and direction of the field are fixed. And that magnitude is this. It's based on the charge density of the plane and that fundamental constant, epsilon naught. So in the problem set that you're going to do when we get back from break, you'll need to apply this idea a couple of times, that the electric field of a plane is uniform. That comes up in a few of the questions. You might need the formula as well, I forget right now. But you probably need the formula too. But you can just take it as given. And like I said, we'll come up with a much better way of deriving this formula when we study Gauss's law. It's very quick. But I want you to start thinking about these uniform fields now, which is why there's a couple of problems about it that I'll be giving you this week. Okay. I think that's everything that I wanted to say. This is probably really long, so hopefully you watched it sped up or skipped parts of it. I'll make sure to put chapter stops in. But that is it. So the basic idea, let me go back here. Actually, I don't like that version. The basic idea is that the electric field, I'm going to put vectors on these. The electric field at some point is the integral of all of the individual contributions to that electric field. And dE vector could be written as k dq over r squared. And then I need to put like a vector in here also. I'm going to use a unit vector, r hat. And most of the time, dq itself is going to look something like lambda dx or sigma d, I guess dA. for area, or rho dV, or something like that. But even though area and volume are either 2 or 3 dimensions, that doesn't mean you have to really do like a double or triple integral, because like the area or the volume, you're going to know one of the dimensions of it. So like the area might be a known width times a varying length or something like that. But regardless of the specifics of that problem, you have to replace the dq with density times an amount. And in many of these problems, the vector nature is going to be important, so you might have to, in order to perform the integral, you might need to take like just an x component or something like that. So that'll involve throwing in a ratio or a trig function of some sort. But that's the basic idea. Extremely similar to what we did with masses earlier, except for the vector wrinkle, which will come up in some problems and not in others. Okay, that is actually it. I'm done talking. I hope you're having a good break. I've been relaxing a lot, and I'll see you in a few more days.